Thank you, Marie, for the exciting science awaiting us. Now we actually get to start with an amazing keynote presentation. Also, just as a short reminder, if seating in this room and on the stairs is full, you can also watch the live stream at the GAN stage. But please note that the Q&A will only be possible in this room. Now it's my great pleasure to introduce our keynote speaker, Pierre Gentine. Pierre Gentine is a professor of geophysics at the Columbia University and director of the NSF Science and Technology Center, Learning the Earth with Artificial Intelligence and Physics. His research focuses on the continental hydrologic cycle, land-atmosphere interactions, and extreme climate events. Using machine learning, remote sensing, and high-resolution modeling, he investigates how rising CO2 levels will alter droughts, precipitation extremes, and ecosystem responses. He earned his engineering degree from Sub-Aéreo in Toulouse and completed his master's and PhD in civil and environmental engineering at MIT. And he's a recipient of multiple early career awards from NASA, DOE, and NSF, and is an American Geophysical Union McIlwain medalist. Today, he will tell us all about latent spaces and their application to weather and climate. Welcome. We're looking forward to your talk.
Thanks a lot. Thanks for the invitation. It's great to be here in this beautiful venue and in Munich as well. I wanted to talk today about latent spaces, so that's very related, I think, to a lot of the discussion. And I've been really obsessed with that over the last couple of years in a couple of ways, for prediction, but also for understanding, and to try to think about how we could also use that as a way to merge different modalities, because that's really what we are trying to do when we think about environmental systems as a whole. And sorry. Need to find my. Just wanted to first thank the team. So I'm mostly the messenger here. So a lot of great people. Some of them got nice faculty jobs around the globe. So wanted to thank them for that first. So over the last couple of years, we've seen an explosion of the use of AI for weather and climate modeling as a whole. In fact, as we speak right now, as of last year, now we are actually using AI for weather forecasts, which has been a huge revolution. A couple of years back, we were just starting with initial proof of concept to try to see if we could emulate some of the physics that we have for physical modeling and for weather forecast. But now some of the weather forecasting that you're getting on an everyday based on your phone is actually based on AI. So that's basically been a revolution we've been witnessing in a very, very short period of time. And some of those models are actually on par, even better than physics-based modeling. So that's really a tremendous progress. In parallel to that, the same is happening, maybe not at the same scale, but to some extent, actually with my colleague Veronica Eyring here from Munich as well. But we've been pushing as much as we could, some of the limits of what we can do in terms of climate modeling. And we have a lot of issues in climate modeling, especially, for instance, thinking about extreme events. Oftentimes we want to represent droughts or extreme event and rainfall as such. And this is an example here showing how we could for instance, better represent extreme events. So this is the distribution of rainfall event across the globe. And on the left-hand side, you can see that the typical standard way of doing physics-based modeling tend to really completely miss the extremes of rainfall events. And by using AI and trying to use AI to emulate the atmosphere and the atmospheric processes, we can do a much better job. So we are much closer to the truth here. So we can really pick up the extremes and the tails of the distribution a lot better than historical standard-based physics-based models. So that's really good news, because now we can start thinking about extremes and extreme events, which is really at the heart of climate modeling. We can also look at long-standing biases that we have in climate modeling. So for many, many years, we've been having this issue also for weather forecasting, by the way, where oftentimes we don't have really the right timing of precipitation. So this is showing you the diurnal cycle of precipitation here across the globe. So this is here over the US. And oftentimes we tend to have this bias where we tend to rain in the early afternoon, but this is not the case in observations and neither in very high resolution simulations. And what we could show is that by using AI, we could actually nicely replicate, to some extent, not perfectly, but quite well, this kind of diurnal cycle in precipitation. And we don't have this bias that might have been annoying, especially if you wanted to go running when you didn't have the right timing of precipitation. Those are things we can start solving as we speak. I haven't checked. We'll look into that. But Really, the bottom line, especially in my group over the last couple of years, we've been really trying to think like, what are we really learning as we go into this kind of deep learning strategy? And really, what is the type of new understanding that we gain through the process? And in some sense, we wanted to see like, how can we open up the black box to some extent? And oftentimes we use some sort of data compression or some latent space. So what is that data compression really teaching us to some extent? And can we use that to also better predict, so what is that latent space? And we're hearing a lot about world models. So why is a latent space predicting better than the regular physical space? So I hope I will try to get into that. And kind of the example that we could have is like the old way of thinking about that. You have some data compression, thinking about images here, for instance, for numbers. And oftentimes we would want to actually decode, some axes, and we would want to actually make sense of some sort of latent representation. So for instance, very, very simply here, you would have head pose on one axis, and then you would have smile as well. So in some other words, can we find the equivalent to that for weather forecast and climate system? Is there some sort of latent representation that could actually make sense and would also improve prediction as we get there? So are there kind of equivalent dimensional reductions for climate and weather? So we're going to get started with a simple case. We are going to be looking at turbulent flows. And I'm saying simple, but anyone who has worked on turbulence would say it's actually very complex, right? And it's complex in different ways. So oftentimes when we look at turbulence, we like looking at spectra. So we look at the wave numbers, and we basically find this typical cascade of scales, and we have many, many scales that are interacting. And obviously, when you have that, people will say it's extremely complex. We need to represent many, many degrees of freedom, and therefore it's very difficult to actually numerically represent that in simulations. The second annoying thing that we typically have in turbulence is it's stochastic, right? It tends to not be deterministic. And this is a typical time series from some observation of a turbulent flow here. And you can see like for wind direction or wind amplitude, you see a lot of these oscillations that are going on there. But the important point is that if you look and you use some sort of smoothing, we call that Reynolds averaging in the jargon, in the turbulent jargon, it tends to be a lot more well-behaved, right, compared to the stochastic component that we have here. So it's kind of telling us that maybe there is something more approachable in turbulence than just the mere trajectories. And my kind of preferred way of thinking, and I've been really obsessed about that for more than a decade, is my preferred way of thinking about turbulence is it tends to be a lot more organized than what we think it is compared to the spectra and compared to the stochasticity that we have here. And if we just look at simulations, we see updrafts and downdrafts and organized structures. We call them coherent structures, right? And I've really been obsessed as to how can we extract that from the flows and trying to actually find something that is much more predictable than what we would expect from the stochasticity and from the spectra alone. So what we are going to do is we're going to take some turbulence simulations. We are going to apply that to weather, but we apply that to many type of academic simulations. And we're going to take this type of pattern here, so some simulations of turbulence, and we're going to decompose that into what we will call a mean flow, so taking the analogy that we have in turbulence, which is called Reynolds averaging. We take like a deterministic component, like some sort of smooth component, and we are going to take some deviation from that, some like those small deviations, like the stochastic component that I showed you before. So you could think about that. This is kind of the smooth behavior and then the departure from that. And that mean component, what we are going to do, because we have a spatial field, it's multivariate, it's highly complex in space and time, we are going to try to reduce that, and we won't use the typical strategy, which is to take a long-term average in space or time. We're going to try to use modern techniques, and in that case, we're going to use what we call a deep Koopman operator. We're going to encode that into a reduced latent space, which is going to be quasi-linear in the dynamics there. And then we're going to unroll that over very, very long time steps. And then we are going to look at the deviation from that, and that's going to be a fluctuating part of the flow, which has to be stochastic, because I just showed you that turbulence is very stochastic. And we are going to model that using some sort of probabilistic or generative techniques. And in that case, we use a conditional diffusion technique. So we are going to have those two components. One, which is kind of the intuition here, is we are trying to get the coherent part of the flow. And then later, we are going to try to get the deviation from that coherent part of the flow. And that's how the architecture looks like. You take a complex field, so it's basically a 3D cube multivariate. We are looking at the atmosphere here. And we want to encode that through this decouplement operator. Then we have this latent representation. Everything is linear, so you can even look at the eigenvalues, and you can think about those modes of propagation. And you can decode that, and obviously you have some compression, so you will have some loss, so it's a lossy compression. So you will have some lossy representation and reconstruction there. And then what we are going to do is we are going to just improve that using the denoising component. So we are adding noise by the denoising, if you will, to actually generate the stochastic component and to get a flow and a representation that looks very realistic at the end of the day. So we have a two-step process. We actually train them together, so it's trained end-to-end. And when we do that, on the left-hand side, you have basically weather, but we are looking at here like sub-seasonal to seasonal prediction, so 40 days plus into the future. At the top is temperature. In the middle is what we call geopotential height. And then at the bottom is moisture in the atmosphere, so think of that as the driver of precipitation. Here, the second column is showing you the latent representation, so this coherence or this kind of low order or reduced order representation of the flow that we can roll out very, very long into the future. And then we can generate, as we go, multiple representations through the conditional diffusion, and we have realistic representation of the future. And as you can see, they look very realistic. You could look at the spectra, you could look, at various things, and they look very realistic, much more so than the typical weather-based AI models that you roll out and become very blurry and very unrealistic over time, such as the ones from, for instance, DeepMind or NVIDIA. They look very unrealistic over a couple of time steps. So this combination actually buys you a lot of physical realism, but also a lot of skill as well. You can actually look at various, components that would actually be related to skill. This is, for instance, some root mean squared error here. This is another indicator looking at the spread of the simulation, the quality of the simulation. So at the top, if you go down, that's better. At the bottom, if you go up, that's better. And you can see that ours, so this kind of coherence, so this combination of the reduced order model combined with the conditional diffusion model can do a good job. So we are basically as performant and competitive with the standard sub-seasonal to seasonal forecasts from some of the top modeling centers around the globe, but at a fraction of the cost. This is a very, very simple model, just to emphasize that there is something highly predictable in the flow that we can pick up using those techniques, and we can actually make it very realistic by using conditional diffusion and generative techniques on top of that. I wanted to emphasize that completely in parallel. So there's been some really nice work by folks at Polymatic, also in New York, and the Flatiron Institute, where they've been trying to look at latent diffusion models, conditional latent diffusion models for physics-based simulations. And they've developed this benchmark data set called the WELL, where they put a lot of different benchmark data sets for physics-based simulations, from Rayleigh-Bernard to like plasma and so on and so forth. And what they could show is using their techniques of a latent diffusion model, which is in that case, it's actually an autoregressive model over time. They could show that they could get very realistic simulations. So at the top is the truth for different types of simulations. And then the third row here is actually their simulation. And you can show that it's very realistic on many, many different criteria and very different metrics of success. And I found that very interesting because it's kind of pointing to the same conclusion, is that there is something highly predictable through this latent representation of very complex turbulent flows. There is something highly predictable about the flow that we can potentially pick up. And I wanted to emphasize what they concluded in their paper here, which is on the archive. They concluded that our results reveal key insights about latent physics emulation. Diffusion-based emulation accuracy is surprisingly robust to latent space compression. Compression serves as dual purpose, reducing dimensionality and also filtering out perceptibly irrelevant patterns. And I think that's quite fundamental, and that's what I meant by those coherent structures. It looks very complex when we look at the stochasticity, when we look at the spectra, but there's something highly predictable in those very complex systems. And deep learning, and especially latent spaces, can really be a way to actually encompass this type of very complex system, and we have the tools now to actually do that a lot better. And one thing that they mentioned that I think is actually very interesting is they said that higher compression can sometimes improve generation quality to some extent. So it's again pointing to the fact that there is something highly predictable in those very complex systems and highly complex chaotic flows. So conclusion being that turbulent flows that are chaotic and stochastic might be more predictable than what we typically expect. And they are maybe more lower dimensional than we expect. Linked to that, we thought like, okay, now that we know that there is something more predictable that we have in those systems, we thought, and this is kind of analogous, if you will, to kind of what is happening in the world model literature, we thought like, can we start thinking about changing the way we are training a lot of those weather forecast-based models? So typically what we do is we take basically many layers of the atmosphere and for different variables like temperature, moisture, and some other variables. And what we are trying to do is we are autoregressively trying to predict the future, and we use different architecture. The architecture at the end of the day is not dramatically important, and we can do a very good job at predicting into the future, but over time, many of those simulations become fuzzy or they become unrealistic, and people have been wondering why is that when we train those models that they actually become unrealistic. And the typical strategy that people have is that they typically define a loss. You can change the loss based on what you have, but basically you have a loss for the different variables and you roll that over time. You can have a loss over multiple time steps, but that's basically an autoregressive strategy. And what we thought, and that's, again, you could say very much aligned with the kind of the view of world models, is trying to think about what if we were to take the exact same architecture, but instead of training in the so-called physical space, the actual space, we were to train the model in the latent space. So we do the exact same strategy, but now we train in the latent space, so this Z space here, and we are going to see what's going to happen, but again, with the exact same architecture, just like apple-to-apple comparison. And what we see is that, and I hope you can trust me from the back, on the left-hand side, when we train this architecture in the physical space, so the standard way of doing that, typically using a mean squared error, but you could use whatever you want in that particular case. Over time, the simulation becomes very blurry and very fuzzy and unphysical, and you could see a very sharp drop in the spectra, especially at high frequency. And that's something that everyone has been observing when they train those models. When we keep, again, the exact same architecture, but we train that in the latent space, instead, what we see is that the spectra remain very realistic over very long time periods. And we can also show that when we start from completely random initial condition, we very quickly get into a state that is very physically realistic. So what it's telling us, again, is that the latent space is really encoding some of the physical realism that we have in the real world, as opposed to when we try to do that in the full complex phase space of the real world. We can check that in other ways. So this is an example here where we look at some typical diagnosis of the system. Typically, we know that when we look at the atmosphere, it has to be in what we call geostrophic balance. So basically, you have a balance between pressure and Coriolis effect, pressure gradients and Coriolis effect. At the top here, U is the wind component that we would have. UG is the geostrophic wind component, and you can see that they are very much alike, so it has to be quasi-geostrophic, especially as you get up in the atmosphere. And we can look again at the two cases where on the left-hand side now you have the latent learned model as opposed to the real space learned model. And again, you can see that the latent space representation is a lot more realistic compared to the observations, which is here on the right-hand side. And we have much more of this encoding of the geostrophic wind, even though we didn't really encode that ourselves, but this latent representation is learning a better representation of the physical system and especially of the dynamics of the system over time. So I think that's important. Based on that, what we thought is that maybe we can use this kind of latent representation to do what people do in practice for weather forecasting. So every day when you're getting your weather forecast, and that's why they are changing on a regular basis, is you do what we call data assimilation. In control, we typically call that filtering. And what it is that you're trying to merge a physics-based typically model, it could be also an AI-based model, but you have a forecast model, and you're trying to bridge that with observations that typically are noisy and uncertain as well, typically from satellite observations, radio soundings, or whatnot. And what you're trying to do is you're trying to merge observations here coming from various modalities or various sources here, and you're trying to bridge that with a physical model and fusing that in the most optimal way so you get the best estimate of the state of the system, because it's a chaotic system, so you're always diverging to some extent. So what we thought is we could potentially start thinking of that as different modalities, right? You have the modality coming from the physical system, so the forecast from the model, and you also have the different modalities coming from the different sensors and different observations and sparse observations as well. And what you could do is you could have a latent representation of all of that and have a unified latent space, very much like what people are doing when they have multimodal type latent representation, right? And once you have that, you could actually start querying that or prompting that or conditioning that, so you could actually get some estimate of the state that's actually consistent with the conditioning that you have. This is very similar to image generation, where the conditioning would be actually generating you an image, or video generation based on conditioning. So we are framing that very much in that framework of observation-guided state estimate, by trying to get the best estimate of the state given something, and typically this something will be the observations plus the prior coming from a model. So the way we are doing that is we again frame that as those different modalities. So we have what we call typically in the jargon the background. So that's the physical model. So we have this free running model, physically based model typically, that is giving us a prior for the estimate of the weather. We have the different observations and the different modalities, again, different satellite observations, weather stations, but also radio sounding. We encode all of that into a unified latent space, and then we get through kind of a denoising process where you would have the denoising process to get to this distribution here, and we would want to decode that to actually get to the best estimate of the state based on all of that. Once we have that, we can very easily do the prompting, right? So it's very similar to prompting. It's just the conditioning based on the observation. So we can bring in whatever we want. Typically, what we will typically have will be the backgrounds. So we will have a physics-based model that is actually free running. So that will be the XB here. And we will have some observations typically coming from satellites or from weather stations as well. We're going to use that as the conditioning. Think of that as the prompting. And we are going to generate on the fly for relatively cheap compared to the standard way of doing data assimilation. We are going to generate some realistic 3D fields of the real world and the atmosphere. And we try that in different ways, and that tends to work quite well. So at the top is the truth. The conditioning will be, say, in that particular case, the middle row here. So that's going to be a coarse resolution model. And then when you have this kind of conditioning or prompting, you're going to get a state that looks a lot more realistic, much more like the real case. So that basically shows that this type of strategy works. We also looked at different things. You could think about super resolution, generating final scale images, because you can do a lot of those things. So those generative AI techniques tend to be very agile, so you can do various things there. And finally, to conclude, so we try to then push that and try to be a little bit more systematic and formulating that a little bit more in what we call the data assimilation framework. So just to walk you through that, so we have two different types of strategies. Typically, we have what we call the 3D VAR technique and the 4D VAR technique. 3D VAR meaning that you have the trajectory of your model. We call that, so that's the left-hand side here, so that's the background here. And what we are trying to do is trying to penalize for the mismatch to the model, right? The physics-based model or some sort of free-running model that you have. We have B, which is a background covariance structure, which is actually weighting the structure of the error that we have in the model. We can actually learn that through historical data. And then on the right-hand side, you have the observation update. So you get some observation, and you want to be as close as possible to the observation. It's formulated in a way where H is what we call the observation operator. You go from your state, X, and you get into the observation operator. So think of that, my satellite is not directly observing what I want. It's actually, you have a transfer operator that you need to invert. So this is typically an inverse problem that you need to have. And then you also have a covariance structure, because those observations can be correlated, and they can be, they also have some particular variance level as well. So we also need to account for that. So that's basically what we have here. The one thing that we did here, so the slight change that we have is we said, instead of doing that in the physical space as what people do, typically we are going to do that directly from the latent space. So that's what you have at the top. You go from the latent space into your physical space through the decoder here, and you encode into the latent space here. And we are going to do a lot of the background. We are going to do that in the latent space, and we go through the observation from the latent to the field, and then from the field to the observation operator. We assume that everything can be has a gradient, so we can actually go down gradient, and we are going to optimize all of that together. The main point being that the big change compared to the standard way of doing data assimilation is we formulate that everything is formulated in terms of a latent space. So we don't work in the physical space, we work in a layer below, which is the latent space. So we work in that Z space. And when that's needed, we can actually generate the physical space, and we can generate whatever is simulated by the sensor. The slight twist to that when we have 4D VAR is we have a window over which we have multiple observations. So think of that, you could have weather stations observations, satellite observations, and we are trying to combine all of that together over some assimilation window. Whereas for 3D VAR, you just do it one at a time. Every time you get an observation, you're going to get what we call an update. So you do this optimization loop at every time step. And importantly, what we see is if we go back to this kind of background covariance structure that I showed you before, we can see that in the real space, we see that there's a lot of correlation. So these red and blue colors are showing you the correlation that you have across the different variables. And you can see that typically many of the variables in the atmosphere tend to be very correlated, right? And that makes sense because if you look at any type of atmospheric profile, between the top and the bottom, or even also in space, we know that there is a lot of correlation, right? The temperature between here and say 10 kilometers from here is going to be highly correlated, right? So we know for sure that there's going to be this very strong correlation. And that's true across variables here on the left, but that's also true across space as well, and across resolution. Interestingly, when we go into the latent space, we can again estimate this background covariance structure and this background covariance matrix here. What we can see on the right-hand side is that there is no correlation, right? And really what the latent representation was trying to do is trying to decorrelate as much as possible those modes of variability, right? So implicitly we didn't impose that, but the best representation, the best latent representation was trying to decorrelate the physical modes, right? And that's again related to the representation that we were talking about before, the fact that the latent representation is trying to some extent to represent physical modes, right? Physical modes of variability, right? So that seems to be the most compact way of doing that and the most decorrelated way of doing that. Similarly across space, so typically we need to have tricks to basically encode the impact of a particular sensor at a particular place, and we can see that it's actually much more localized on the right-hand side in terms of spatial correlation. So we can directly use the observation at a particular space. When we use this strategy, what we can show is that we can systematically improve over the standard way of doing 3D VAR or 4D VAR, so this standard data assimilation, again, that's being used in weather forecasting every day. So every time this is a reduced root mean squared error, we can see that for different variables, so geopotential, temperature, and moisture, we always basically go down, whether that's for the instantaneous 3D VAR or for the assimilation window 4D VAR. And interestingly, it goes even more down when we look at the 4D VAR, which is this assimilation window. And the reason for that is that this latent representation tends to remain very linear, and I'm going to show you that in a moment. And so it means that we preserve a lot of the self-consistency over time. So this encoding is not just trying to capture the modes of variability, it's trying to keep them as linear as possible. So it's not too far from what I showed you earlier with the Koopman operator, right? We impose that as a Koopman operator, which is this linear operator, but implicitly when we have some latent representation, it's trying to be quasi-linear to some extent. And that's what we can show when we look at some basically perturbation. This is a perturbation analysis of that latent space and the impact. And we can see the main point being here that it's quasi-linear. And again, what it's telling us is that the best way to encode the dynamics is to encode the dynamics in a way that is quasi-linear, and those modes can then propagate and remain very coherent, right? And that was the point I was trying to make earlier, is that we have those coherent structures and we are trying to preserve them, and the best representation of the system is to create that and to encode that into a latent space that remains coherent and not to destroy the coherence between those modes. And most likely this is the reason why we could predict at very long time horizon in a predictable and higher accuracy way. And wanted to emphasize one more thing, is that when we do the inversion, typically for data assimilation, we need to have an inverse of the background covariance matrices, and that tends to be very, very computationally expensive. But on the right-hand side, I showed you that in the latent representation, we have a quasi-diagonal representation, right? So it's straightforward, and it's obvious to invert that, right? So that becomes very, very cheap as opposed to becoming very expensive. So we have two advantages of doing this latent data assimilation. We can encode in a way that is more efficient, but also more accurate as well. So basically, it's a win-win. Just to conclude, I wanted to show that there are times when this latent representation might be insufficient. This is a case for precipitation here, where we have some radar reflectivity here. The truth is on the left-hand side here. This is simulated, so that's the background from the model. And when we try to do this kind of latent assimilation, in that particular case, it doesn't work so well because things tend to be a lot more stochastic, right? Rainfall tends to be extremely sporadic, especially convective rainfall that we have in the summer. And in that particular case, there's not a lot of coherence. You know, like the thing that I told you before that is highly predictable, in that particular case, there isn't a lot of that, right? So in that particular case, that would be a failure. But otherwise, when you have things that are more predictable, when you have some coherence in the flow, that's a case where you would see a lot more predictability, and you could actually pick that up with many of the techniques that we have now. So just to conclude, so this kind of, I've been very interested in that latent representation as a way to improve the skill of prediction across scales. And what it shows is it can lead to more skillful prediction and also more efficient data assimilation as well. And I would say it's actually more than just data compression. I didn't show that here, but we are trying to use that a lot for understanding as well, trying to understand those modes of variability or things that we typically don't pick up in standard models. So with that, I'll be happy to take any questions, and thank you for your attention.
Yeah, thank you for this very insightful talk. We have a bit of time for Q&A, so please just raise your hand if you have a question. And yes, I see Carsten over here. No, there is the mic.
Yeah, very impressive. I can imagine that the dimension of your latent space is crucial to fulfill this linearity, right, that you need for the proper prediction. How do you get to the right?
Yeah, it's trial and error. I actually have a backup slide, but maybe it's difficult to show here. But exactly about that, like trying to see how we can push this compression. You know, it goes along as well, so it depends. Like if we just have a deterministic model as opposed to a generative model, if you have a generative model, you can actually buy yourself a lot of things on the generative side of things, and you can push the envelope of the compression. But if you have a deterministic model, that's definitely a huge trade-off in that particular case.
Yeah, there's a question from Fabian here.
Hi, Pierre. Very interesting. This was mostly now for weather, not for climate, but I would assume the latent space dynamics maybe even would hold on the climate side?
Yeah, so actually that's some work we are trying to do with Veronica Eyring. So yes, but it's a lot more complicated, I would say. So the one thing is that when we look at long-term climate, you have what we call counterfactuals, right? Changing greenhouse gases, right? And you would want to see what is going to be the change on your distribution, so this out of distribution prediction, right? So I think it calls for, it's not really, I mean, it's not too far from world models, but there's like action or counterfactual, so you're getting there, you could say.
That was exactly my point, what I asked, right? So I wanted to ask, like, where can you do now, perturbation, essentially counterfactual in weather, I guess? Not
weather is difficult, yeah. So that's why.
But don't people sometimes build, like, I don't know if they change some local thing and maybe then local weather patterns at least? Or
that's a very good point. So
I would long term, right?
Yeah. So I would say for climate we are thinking a lot more about actions, right? For weather you're more observing and you just want to say. So that's why we typically frame that in terms of like just trying to estimate the state, right? And so we don't really have the action component of world models, you could say. But when you think about climate, this is much closer. And another way, so first, humans are doing that. We are doing counterfactuals on an everyday basis, right? We are putting greenhouse gases. But we did that as well for aerosols, right? That's actually very interesting. For a long time, the climate change signal was really not very visible because we had a lot of aerosols that were masking some of that. And then we had some regulations, and all of a sudden, a lot of those things actually changed, especially at the regional scale, but also at the more global scale. And it's very clear that those actions have a very clear impact on the state.
Just my last thing, because we have some latent space diffusion that helps us ask counterfactuals, so I think that could
Yes, yeah, I think you're right. There is, I mean, if I may, there is, and I think it's actually really missing in the weather, I mean, we are actually working on that as well, but there's this fundamentally multi-scale prediction, right? If you really want to be thinking about very long time scale, it's more than just rolling out weather, right? Because, as you said, there's going to be actions on the way, right? And those actions are going to change things. What people see, which is very interesting, is when they use so-called foundation models for weather and climate, they are really just weather models to a large extent. What they do is they drift back to the weather they were trained on. So they tend to always have a cold bias when they are used in the future, which should be warm.
Hey, thanks for the talk. I was wondering, do you think precipitation is just hard to represent in the latent space, or is it actually impossible? Like, what's the intuition behind it?
I think it's very difficult because it's very, it's both chaotic and stochastic, right? I mean, the way you form cloud droplets is kind of random, to a large extent. So it's very difficult to know if it's going to rain here, it's going to rain like, like 500 meters down the road or something. What you can do, though, is you can, I think, or that's what we are trying to do, is you can represent that as a generative process, right? And that's a lot easier, right? You could just say statistically it's going to rain here. That's the only thing you can do, and you could have ensemble generations, or you could Monte Carlo that so that it looks like reasonable, right?
Thank you.
There is typically this double penalty issue where your model is simulating that it rains here and then it rained here, and you have like double penalty, So the typical solution is the model will have a very smooth behavior, because it's, you have this double penalty issue. So that leads to a very, very poor model, deterministic model.
Yeah, yes.
Okay, thank you very much for a very nice talk. I have a question. You mentioned about the autoencoders that we know they are somehow generative model, means you compress your data and try to regenerate from the other leg. How you control and how you guarantee that in the output you don't have any new feature for unseen data, I mean?
Good question. We haven't really checked that, yeah. We just check, I mean, standard loss. Yeah, we haven't checked. I mean, we look a lot at also like physical realism as well, like spectra and things, but we haven't checked that we generate new things. That's more what I'm checking with agents these days with coding.
Because you've mentioned you are doing denoising and compression somehow, so definitely you will have some new features for unforeseen data. And I have the second question very shortly. What data compression rate is interested for your data? How big is your data, and how much you will be happy when, how you will be happy how much you compress your data?
That's a very good question. It depends very much. Sometimes the compression is actually not that small. Sometimes it's more like trying to make things more linear to a large extent. So there are times when the compression is actually very minor, but there are times when, it's quite big. You could go 100, I would say. I mean, quite big for our standards, I would say. But it's always a trade-off, with quality of reconstruction as well. But there's also a lot of redundancy in the data that we have, Maybe one thing I didn't mention, but there's also on the generative side of things, as I mentioned in the first slide, we are very interested in extremes. So also with colleagues, at UC Irvine, we're also very much looking at the tails of the extremes. So, for instance, there are techniques so that you could have a diffusion model that is not based on Gaussian noise, so that you have better tails of the distribution, because we want to have those very, very long tails of the distribution.
Yeah, thanks.
A question over there.
Thank you very much. two questions. One is, you said what we learn from the physics is that the flow, with this kind of flow, you have low dimensionality when you have turbulent flow. This is what we learn from these kind of models when you compress the data. This is what we obtain from this analysis. That's right?
It's lower than we expect. I would frame it this way, yeah.
Okay.
I'm not saying it's simple, turbulent flows remain very complicated. But what I meant is that it's more predictable than we expect. Like that coherence, you can, it's a bit more, whatever, we could get into the weeds. But there's one component as well, which is that even those coherent structures, they should be chaotic, right? So you should have some divergence of those, like even the big structures should be. But there's a lot of times when we look at standard methods, we focus a lot on the details, and the details actually are not that relevant. We can basically make them up.
Okay, so that means that's valid when I have a big picture, let's say, for a macro scale. When I want to go down in the macro scales, then I must be more careful when I make this kind of analysis.
Yeah, it depends on... Okay. The one thing I didn't show, but I think it's quite fundamental, is that so in the version I showed here, we don't have a feedback. But we know in physics that there is a feedback between the small scale and the large scale.
Yep.
So what we did is we have another version of the model where we have this kind of big coherent, like this deep Koopman operator. Then we generate the high resolution field like on the fly, and then we feed that back. Okay. So we have a feedback. And obviously, as you would expect, it's always better than the standard model. And again, you could say it's kind of another way of showing and demonstrating something that we know very well, is that in turbulence, that the fine scale is important for the large scales.
And get critical states and so on, and perhaps self-organization.
Yes.
Final question, how long was the training or the period of time where you obtained the data to train these models? It was several years?
No. It was very, we did it at relatively coarse resolution, and that was the point, is just showing that even relatively simple architecture trained by academics could be relatively competitive. But it was not, we were not really looking at performance per se, it was more like proof of concept that, there is something we should be able to characterize in those systems, and and that should be useful for prediction.
Okay, thank you.
Thank you.
We have a question up here from Martin.
Yeah, thanks a lot, Pierre. Great talk. Quick question, not coming from the weather field, but coming from the health and organism life science area. If you think about development of organisms or organoids, whatever, if you think about disease, you always have a definite number of players, which are in some cases chaotic, in some cases organized in a stochastic way. Mm-hmm. Not similar, but in a way, maybe also their latent space might be interesting. I'm pretty sure you have been approached by people from that area, if we can make use
Not really,
of those.
but I would be very interested.
Okay.
Yeah. We have the two flavors, and it's actually interesting because a lot of people are confused between chaos and stochasticity. They are not the same. Look it up. But it's actually interesting because we have those two flavors, right? I mentioned, for instance, microphysics and cloud droplets, how we create precipitation. This is very stochastic, like how particles and droplets actually are interacting. But we still have this very strong dependence on chaoticity, this chaotic behavior and dependence on initial condition. In fact, we are working with a postdoc. We are wrapping up a paper showing how we can better learn chaos from data. And it's actually more subtle than what we think. It's not just like training on long rollouts. There are things quite fundamental about making sure we can get the right Lyapunov exponent. So I think those two can be combined somehow. So you have the chaotic component, which is actually very crucial, and that's why now it's still a struggle to use AI-based model within data assimilation systems, because you need to get the chaotic behavior really well. Like you need to get those gradients really well. That's very important. We don't have them so well now because there's a lot of cross correlations and artifacts, that are just spurious, from the training. Anyways, yes, I think this is quite very important, I would say.
Question over here.
So thanks for the talk. I'm more interested actually in your technical tricks. I think everyone that is working with this latent space representation knows that it's quite hard actually to keep the dynamics and avoid the latent space to collapse. And if you look at JEPA, for example, there is some things like SIGRAG, for example, that you can make this stable and so on. And in your particular case, for example, which are this type of tricks that I'm pretty sure that you and your team has faced?
Yeah, I didn't show that here. So it was actually on the slide, but a little bit slow. The one thing we do is we first encode, and we use as a prior, and we encode based on some best estimate of the past, of the historical past. So that's how we can get a relatively good representation of the encoding into that latent space. And then we do that training. But the training, it's a bit detailed, but it's actually important. We formulate that very similarly to 4D VAR. So we actually include this kind of covariance structure. And why is that important? Is because it's a way to make sure that, first of all, oftentimes we get data and you have like random noise in the data. And that's really, I think, I don't know, it's difficult to show, but I would say this is what is destroying over time the crispiness or the quality of the forecast, because you get this little noise and then it will propagate and then it will destroy things. I tend to think of that like lasers. You know, you have like decoherence over time and you need to keep the coherence of the laser, right? And when you get into the latent space, so first you have the prior from the encoding, which is based on historical good quality reconstruction. And then we also weight things based on this covariance structure, and that tends to work very well, and that preserves a lot of the physical consistency. Sorry if I went too fast.
Okay. Do we have any further questions? Okay, maybe I can ask like one last question. I was wondering, what's your take on what's the future use? How do you see AI methods being used in weather forecasting and so on? Do you think it's mostly to replace kind of expensive model components, or more for really gaining some physical understanding, like you also showed with the compression of the latent spaces?
I mean, it's quite clear that AI is eating everything for weather, right? So it's just, I mean, now we have very good weather prediction. We still have physical models for that part, you know, like for the data assimilation, but you would expect that that's going to be solved. And I mean, those models are just so much cheaper, right? They are 1,000 times or even more cheaper than the regular model, so that's a no-brainer. Like you can run the model many, many times. You can look at extreme events, so people look at NVIDIA, colleagues at NVIDIA. My friend Mike Pritchard, who's now at NVIDIA, I mean, they look at like a lot of realization, so you can look at the very tails of the distribution. So I think that's quite clear is going to get there. For weather and the understanding, I think there are fewer people, but it's very interesting. For instance, I have a smart master student. She's looking at like poking the latent space and looking at tropical cyclones and how we can actually poke them. And maybe people will think about that for maybe geoengineering, like steering tropical cyclones so they don't hit the Caribbeans or something. So I think it will be pretty cool. Like, looking forward to that.
Cool. Great. Well, thanks a lot, Pierre, again, for your,
thanks so much.
your nice talk. And